Well, welcome everyone. So we will be starting today the lab for CL 801, right? And we will be doing various experiments. So as it's an advanced chemistry laboratory, so we will be definitely doing many experiments which are of good level. Now what we are going to do today? So we are going to do an experiment which will be conducted in multiple parts, right? Multiple parts. So that's the whole idea. So what is it? It is to go from crystallization to structure solving. Now in your CB601 we had already spoken about like protein X-ray crystallography. So you already have a feel for what protein X-ray crystallography is all about. How do we do it? We will learn practically. How do we collect the data? That also we will see. And then how do we process the data for the single crystal? That also we are going to see. After the data is being processed, then how do we go about model building and refinement? So that is the whole exercise. So that's why I said this entire experiment is one experiment, but it is going to be in multiple parts. So from the course perspective, each part you can write it as a single report, small report, and then as the thing which you had done in your lab report in this 5th semester, there is no obligation like that. It's up to you, how do you want to report the data, yeah. So there is no obligation that you should be writing in a particular journal format. No, it's not going to happen here. So can we get started? So now there are multiple steps what we are going to follow. The first thing is the siliconization, right? The siliconization, right? Siliconization of what? The cover slip, right? Now why we are going to do the siliconization of cover slip? Before I get into the nitty-gritties and we do the siliconization, let's first understand how do we crystallize the protein, right? How do we crystallize and what exactly do we mean by crystallization? Now if I tell you one thing, tell me if you agree or disagree. Crystallization is nothing but a way of concentrating anything. It can be a salt, it can be a protein. Would you agree or would you disagree? Yeah, pretty much, right? So whatever is there in solution, you are crystallizing out of that solution, right? So the crystals are really high molar solution. They are so high in concentration that they are solid, right? They appear as solid crystals, and indeed they are solid crystals. For salts, yes, they are pretty strong. You can handle them with carelessness. No problems with that. Proteins, they are soft guys, right? Little bit of touching here and there and they might shatter just below your nose. You have to be very gentle and delicate when you are handling the protein crystals. Now how do we understand the protein crystallization? So there is a plot which I would like to draw. If I say a precipitant concentration, and here I plot like protein concentration, right? Now what is a precipitant? Now precipitant is anything which dehydrates, right? Now pretty much like if you have gone on a night out party and boozed on and had a nice alcohol, you feel dehydrated, right? Because your alcohol is a dehydrating agent, right? So then what happens? So then similar things, if you can expose your protein against the precipitant, yes, so then what happens? Your protein starts to concentrate. Concentrate how? Because it is taking away the water molecules from the solution, the protein solution, right. Now, if we have some system, what kind of systems we will see in a minute, some systems where you have like protein in the soluble fraction, nice clear solution in a soluble fraction, right. So, let us say from this left side of the line you have some soluble fraction, and slowly if you start to dehydrate this protein solution, then happens what? It starts to concentrate, you are dehydrating the protein solution, taking away more and more water molecule. So, happens what? Then your protein starts to concentrate. Concentration, in concentration what happens? All these protein molecules will start to come closer, right, they will start to come closer, right. So, you will slowly as and when the precipitant concentration is happening for a particular protein precipitant concentration, slowly your protein concentration goes up, you start to concentrate, right. Now, at a particular concentration, the concentration becomes so much that you go into a nucleation zone. Nucleation zone, right. You start forming tiny nuclei which you cannot see with your naked eyes, right, not even in the under the microscope. You won't be able to see it. Normal optical microscope, you won't be able to see it. They are so tiny. They are there in the solution, but not visible, right. So, they have actually have come together to form those little structured clumps, right. If I should try to simplify, yes.
Why the nucleation curve is on the right, on the left?
No, see.
At a particular concentration, specific concentration,
Yes.
the protein concentration is low for nucleation and high for solution.
Yeah, correct. So, it is just the way to show you over here. So, right now how do you see? Now, protein concentration if you would see like this over here. So, for a particular say precipitant concentration like this. Yeah, sorry, my bad. Soluble. So, the protein has to be soluble and then slowly it moves to the nucleation zone, and this happens to be your precipitation zone. Yeah, thank you so from soluble, then your protein starts to concentrate, it moves to the nucleation and then moves to precipitation zone, right. So, I wrote the wrong thing, right. If you concentrate too much, your protein might simply precipitate or aggregate, and this is what you do not want. You want a nice single crystals to form.
But sir, this precipitation would occur at higher concentration of precipitant, right?
Which one?
Precipitation should occur at a higher concentration.
No, see, precipitant for a given condition, the precipitant concentration is fixed, right. So, when you set up in different conditions, every condition has a certain concentration of precipitant fixed. Let us say I am working at, say, a classic example of precipitant is polyethylene glycol, PEGs, they are the polymers. Let us say I am using PEG 5000 as a precipitant, PEG 5000, it is a reasonably big molecule, medium size as far as the PEG is concerned. I am using 30% PEG. So, I am saying okay 30% PEG, now I am fixed here, right. I am not changing a precipitant concentration for a particular condition. I can have another condition with 40% PEG, right. So, now happens what? And you will see when I will tell you what exactly we do. We start with the solubility zone, right, the soluble fraction. We start with the solubility zone and then we let it equilibrate, right? Those nitty-gritties I am going to tell you in a minute, right? So happens what? For any crystallization, you start with the soluble zone, then you allow it to equilibrate, you slowly allow it to dehydrate against the precipitant. Then slowly as it dehydrates, it moves up, the protein concentration moves up. So in some sense you hit the nucleation zone, and this is where you would like the process to stop. You get nucleation, and then that nucleation becomes bigger crystal, single crystal, which you can handle, and you want to collect data. You do not want your system to fall into the precipitation zone. Yeah, you have to stop somewhere here where you get a reasonable size crystal. From here to here, maybe you would like to go, not beyond this line.
But
Right?
you said in nucleation zone we see very small particles.
Correct. So then the bigger crystals are the bigger nuclei. So see, when you are doing like this, this is the place from just at the interface of solubility zone and the nucleation zone, the fellows are very small, the small tiny nuclei. Then those nuclei are going to come together and clamp together. Now if for the clarity's sake, if you want to say, you can have another line which you will not see in the textbooks. You can call this part as the nucleation zone, and then this particular region as the crystal zone, if you want to have a clear distinction, right? But then in the textbooks, even from the formation of the small nuclei which are invisible to the diffraction quality crystals, they all come under the nucleation zone, right? You do not want to land up in the precipitation zone. Now if this figure is to be believed, any protein can be crystallized, right? Because you just have to start with the solubility zone, then you will slowly start let it dehydrate, and then it will land up in the precipitation zone, right? But unfortunately God is not so merciful, right? So happens what? We have scenario something like this. So you have precipitation zone, yes, we have solubility zone, yes, nucleation zone, extremely small. So there most of the times there is a from solubility you straight away go to the precipitation zone from here, or from precipitation zone you can also have the soluble from, if you see precipitate at one point of time and then after some time the precipitation is gone, all of those kind of things can happen. Your area of interest is extremely small, Now to give you an idea like how it goes from protein cloning to crystals, right? I will show you another graph. Can I rub this off?
Sir, what's the area between the precipitation and
This triangle?
no, sir, the above area?
You again can say like so from solubility, actually I should be drawing something like this. So from solubility to precipitation you can go straight away. And most of the times you see that kind of scenario that proteins just simply precipitates. It just simply precipitates, right? Now what happens if I give you an idea why that nucleation zone is so small, right? If I, let's say I start with 100 targets to begin with, right? So if I have to find the structure of any protein, then happens what? Then I have to clone it first, right? Because I have to purify protein, right? So I need a clone at the DNA level. So I choose 100 targets, right? Out of those 100 targets, maybe you are able to clone 95. 5 at least, and this is a very optimistic picture, right, very optimistic picture that you are able to clone 95, right. When it comes to expression, right, whether that protein is in soluble fraction or not, right. So, from 95 you drop down to 50, right. Whether you will be able to purify it or not, you will drop down to somewhere around 35, right. Purification as in you need a homogeneous solution, right. Homogeneous solution, of course you do not want different species, and also you do not want different oligomeric forms of a particular species. Let us say if I am wanting to purify protein A, then I want only protein A and only in one form. If it is a monomer, then the entire solution has to be a monomer. It should not be like you get a different aggregates of protein A. It does not work that way, right. It is very difficult to crystallize such proteins, not impossible though, but it is difficult, right. And then let us say if I have a homogeneous solution, soluble protein, very nice, pure, purity level should be 95% plus, right. We really need a very pure protein, 95% plus. Now, if I have those ones, how many would crystallize, right? How many would crystallize? Extremely optimistic, 20. Yeah, if I tell you the reality, then out of these purified you might be able to crystallize only 10, right. Crystallize as in the diffraction quality crystals. You might get clusters, needles, all of those things are possible, but getting a diffraction quality crystals out of 35, then you will get come to only, let's say, 10, right. Once you have the data, diffraction quality crystals you have got, once you have the data, from there how many you will be able to solve? Let us say around 7. Sometimes there is twinning in the data and all, so this is for the advanced level if you really want to do it. So you get the multiple intergrown crystals, so the data becomes very cumbersome to say process and solve the structure. So that they are the problems, but let us not go into it, that is not the mandate of our lab. Once you have it, then probably 5 structures you will be able to deposit, right. 5 structures you will be able to deposit. So you start with so many stuff, and here now good thing is like we have more than 170,000 structures in the PDB, protein data bank. So then you can imagine how many people are working on the structures, and every Tuesday the PDB numbers data bank updates its numbers, right. But it is definitely more than 170,000. So there are so many targets which people are working upon right now as we are speaking, right. So that is why that small triangular nucleation zone which I had drawn in the previous say graph, it is because of that. Practically we see very small nucleation zone, right, and moreover crystallization is an empirical science. You cannot predict whether my protein is going to crystallize or not. You have to do it to see it. Even if you do a little mutations in the in your protein, treat it as a new protein and do the screening from the scratch, right. So if you know that a particular point mutation is going to affect the structural integrity of the protein, then you treat this your new mutant also as a new protein, and then you might have very often you have to do the entire high throughput screening for getting the starting conditions. Yeah, you cannot say okay, my native protein has crystallized in particular set of conditions, then just it's a point mutation. So I might just get it. You might be lucky. You might be lucky, but no guarantees. No guarantees, right? There are so many parameters which affect the temperature it affects, then the precipitant concentration it affects, then how fast you the crystallization happens. Everything affects the final diffraction quality crystals. Okay, fine. Now, how are we crystallizing the protein? That's extremely important, right? How do we crystallize the protein? There are, yes?
We also have a class of proteins which don't have any tertiary structure, which we call intrinsically disordered proteins.
IDPs, yes.
So they are sensitive to the environment, like the structure is sensitive. So are we able to crystallize those also?
Very tough, very tough. And IDPs, generally those kind of proteins are not very big. So I think the NMR would be a say the technique of choice over there.
They also tend to aggregate.
Yes, and it forms a heterogeneous clusters, right? So then for crystallization, in crystallization we want what? The same unit repeating over and again. But if I have a monomer, dimer, trimer, tetramer, oligomers in the solution, then you won't get crystals.
Crystallizing actin must be very difficult.
Oh, nightmare. It's nightmare, right? Anyways, so how do we crystallize the protein? So there are different protocols, and this is what we are going to see now. What are the different protocols which are currently available? So I am going to tell you all, say maximum of them which I am aware of. But let's see. The first one is the very classic way of crystallization is the vapor diffusion. And this is what we are going to do, the vapor diffusion, right? Now, in vapor diffusion, there are two ways of doing any experiment. It is sitting drop and hanging drop, right? Sitting drop I am calling it as SD, and hanging drop I am calling as HD, right? And in sitting drop, what do? You have a well scenario, something like this, right? Okay, and then you have your precipitant, right? Do I have a different color? Can I have another colored chalk? Yeah, I have a white colored chalk, but I am not sure if it's visible. It's very, no, it's not working nicely. Yeah, yeah, give me one color each. So let's say I have a precipitant in it, right? Then I also have, or rather than calling it as a precipitant, I will call it as the crystallization condition. Crystallization condition. I will tell you in a sec what this crystallization condition is. There is a bridge. Of course, the precipitation, this crystallization condition solution is not flowing into the bridge, right? And then you set up the drop, the protein drop here, right? And then you put the protein here and put the, say, let's say if you are putting 2 microliters of protein, then you put 2 microliters of your reservoir solution or the crystallization condition solution. Yeah, we call this as reservoir, where you fill up the crystallization condition, and then you put 2 microliters of this and 2 microliters is this. So you get like 1:1 ratio, and then you seal it, and then you seal it. Okay, I am going to come back to this 1:1 ratio one more time because we are going to do much more than that, right? And then you let it stand, you do not disturb it. So then what happens? So it equilibrates. So there is an equilibration of, so where is the higher concentration of precipitant now? in the reservoir, right. Now let us say my protein concentration was 10 milligrams per ml to begin with, just for example, and my precipitant concentration was 30% any PEG, right. Let us say PEG 5000 again for example. When I mix them in 1:1 ratio, my starting concentration of protein becomes how much? 5. 1 microliter of protein solution, say 2 microliter of protein solution and 2 microliter of reservoir solution. My protein concentration becomes 5 milligrams per ml, right, and my starting concentration of precipitant, which was 30% in the reservoir, has now become 15%, right. So if you could see, the more concentration is in the reservoir, right. So which will get dehydrated, the drop or the reservoir? And moreover, the drop is not that big that it can dehydrate it, right. The reservoir is typically like 500 microliters or 0.5 ml, and drop is like in total it is like 2 plus 2 is like 4 microliters. So it is small any which ways. So it cannot have the dehydrating effect on the reservoir anyways. Even if it is high, you start off with the higher precipitant concentration. But any which ways, you start with the lower concentration of protein, low concentration of precipitant in the drop, and then the drop dehydrates, because there is always an equilibration, right? Something like this. There is an equilibration happening, and then the solvent molecule will go towards the reservoir because of this equilibration, and as the solvent will diffuse towards the reservoir, it gets concentrated. So that is my sitting drop. So hanging drop is again a vapor diffusion. That is what you say, the vapor diffusion, right. So the vapor diffusion, so you have two ways of doing sitting drop and hanging drop.
So why do we even have the reservoir in the first place?
Without any precipitant, how will you dehydrate?
Just on the bridge we will have the precipitant with the protein.
No, then it won't dehydrate, no. So it will dry out, right. So see, if you say you put the precipitant in the drop straight, and you think that now the protein will dehydrate, right. The problem number one is like your protein solution of course will move towards the precipitant, let us say PEG, but then you already had put in something which is not going to crystallize, right. PEG is not going to crystallize here, and even if it forms a jelly, it won't diffract, right. So you want only the protein to dehydrate, you do not want the PEG to dehydrate or crystallize, right. So in the hanging drop, what happens? You have a well, you again fill it up with some reservoir with say 500 microliters, then you have a cover slip. And then you set up the drop like this, yeah. Practically how do we do it? We will see in the section how to set up the crystallization, but then drop is inverted onto the reservoir, right. And then you have equilibration happening, and then this drop is going to dehydrate, right. So it is going to be like, again you do the same thing, say 2 microliters of protein and 2 microliters of reservoir solution, and then you invert the cover slip onto this reservoir, and then you seal it again. How do we seal it? So for sealing we use something like this vacuum grease. It's quite nice way of sealing things, quite universally used, yeah, universally used, and then hopefully you will hit the nucleation zone, right. You will hit the nucleation zone. That is the whole thought process. Now, we have this two ways of doing say vapor diffusion, and what we are going to do today is hanging drop method, right. It is very classic, it is very classic way of crystallizing proteins, right. Although we are not going to do it, but the other ways of crystallizing, one I am just going to mention you some of the names is the microbatch method. Yeah, and in the microbatch what do? You take the well, so a well as in you take a plate which is having the 96 conditions, yeah, in the 8/12 format, yes. So then you take, I am showing you only one well from the top point, you put your protein and you put your precipitation, your condition, say 1:1 ratio if you had decided 1:1, and then you cover the drop with some oil like paraffin oil. Now paraffin oil is expected to be non-permeable, so it won't allow the liquid to go out, but practically that does not happen. Eventually your this drop, the condition and the protein drop, it slowly starts to dehydrate, yeah, because of the evaporation, not because of the vapor diffusion. There is a basic difference is in vapor diffusion it is because of the equilibration that the dehydration is happening. In microbatch it is because of the evaporation, the drops get dehydrated, and slowly you hope again you might hit the nucleation zone and might get crystals, right. Practically setting up microbatch plates using robots is lot easier, lot easier.
There is fat plus protein.
Yeah. Now I have been using this term, the crystallization condition. Now what is this crystallization condition, right? It is a solution. If I am saying crystallization condition, every condition is unique. Now it is a solution. Now solution consisting of what? It can have these many things: salt, buffer and precipitant. Right. So it typically has salt, buffer and precipitant. There can be conditions where you have only buffer and precipitant, right. There can be also possibility that you have a very high concentration of salt which can act as a precipitant, right. So if you want to dry something, what do? You put it in a salt, right. So if you take an apple, you put it in a bag of salt, what will happen? It will dehydrate, it will wrinkle out, yeah. So you will start having a wrinkly apple because it is being concentrated. This is the experiment which you can easily do. Take a grape, put it in a take a say a small pot of salt, right, fill it till half the level, put the grape and then level it up, right, with the salt. After a few days your grape will become a dry fruit, of course salty, right, salty, but then it will have that form of this resin, it will come into all the water which is there will be absorbed by the salt. So your salts are good dehydrating agents, right. So and especially the places where you see that it is more salty, you really feel dehydrated, right, you feel dehydrated, okay. So buffer, of course, to maintain a pH, right, to maintain a pH it is required, and then you have the precipitant, because without precipitant your protein will not concentrate or dehydrate, right. Okay. So now what's the another way of crystallizing thing? is counter diffusion. Counter diffusion technique. So in that thing, and it's I mean there are very good videos if on YouTube, if you say Granada crystallization box, right, Granada, yeah, crystallization box, so then you will know what this counter diffusion is. To just quickly sum it up, all the things you can find in that video is hardly like 10 minutes video, it's not very long. So you have those capillaries. Now if you put capillary into the protein solution, what do you expect? It will be sucked up because of the capillary action. So if you have this capillary, yeah, you put in a protein solution which is like red, and then it will be sucked up like this, right? You seal this capillary from this end, right? You seal this capillary from this end, and here what do? You have low density agar, the jelly, low density agar, right? And that low density agar, how do you make it? You make it along with the precipitant, right, in water. Oh, sorry, my apologies. So you make it in water, low density agar, and then you puncture with the capillary this agar, right, and then you flood above this agar surface with some precipitant solution, or say crystallization condition or any precipitant like PEG solution. Now what happens? Slowly this precipitant will come like this, so that is my capillary, like this, and will go into, because of the capillary action, right. It is a low density agar, so it is quite porous in nature, right. So then it will go slowly. So actually along the length of the capillary you will have the precipitant gradient being formed. Where do you think the precipitant concentration will be the most? Here or here? At the lower end or the top end? Huh? No, see, first again carefully listen what you do here. You have this low density agar in water, you make it, you puncture the capillary already which is having a protein, right, no precipitant has come right now. Then you flood the above level, the level above the low density agar with some precipitant. So the precipitant will come and diffuse like this. So the lower end will have the higher concentration of precipitant, and as you move above, the concentration will go less. So this is a way of moving on the nucleation zone, right. So you see the on the phase diagram. So remember the first diagram, I am going to come back to that diagram again, where I had showed you the solubility curve, then the nucleation zone, and then the precipitation zone. So that particular thing is called as phase diagram, right. So you move on the phase diagram, hopefully at some point you hit the nucleation zone. There are very many different ways of crystallizing protein, but let us not get into all of the techniques because that is not our mandate for this particular lab. So we will come back to the phase diagram and what we are going to do. Yeah. So I am going to redraw the first diagram again. So what did I plot on the x-axis? Precipitate concentration, precipitant concentration, and this is like protein concentration, right, this way, right, solubility zone, right, and then that's my precipitation zone. Right. So Okay. So, what we are going to do for the practical, we are going to set up crystallization of egg hen white lysozyme. So, that is our target. There is a model system where to learn crystallization. If you want to start as a beginner, you start with egg hen white lysozyme. Hen egg white lysozyme, right. Now, it's a very standard protein to crystallize, right, and the combination what you use to crystallize, it is like sodium chloride and acetic acid, right, that's it, salt and buffer.
That's the precipitation.
Yeah, the salt acts as a precipitant over here, right, sodium chloride and acetic acid, right. So, what we are going to do here, so we are going to have, so use the crystallization plates. Can I have one of the crystallization plates? It's here, right. So, it's a excuse me, 24 well crystallization plate. If you say it is 4 over here and 6 over here, that makes it 24 well, right. So, this kind of plate we use to optimize the crystals. So, for high throughput screening, you have these 96 well plates which you use the robot to set up crystallization for you. Okay. So, if you have this 24 well plate, you have 6 on this side. So, if you would see, it is like A, B, C, D written like this, and it is 1, 2, 3, 4, 5, 6 written like this. That is the cover. So, now it is more visible, it is A, B, C, D and 1, 2, 3, 4, 5, 6. So, every well is uniquely labeled A1, A2, B, A3, up to A6, and then B1 to B6, C1 to C6 and D1 to D6. So, every well is unique, required because you need to document. We will come to that documentation after I am done with this entire crystallization stuff. So, what did I say? The chemicals which you will be using for crystallization, it is like sodium chloride, right, and sodium acetate. Now, sodium acetate is your buffer, right. So, crystallization condition, what did I tell you? It is salt, buffer and precipitant. Now, in this case, your salt itself is a precipitant, right. So, you are not adding a separate precipitant. There are also conditions like using polyethylene glycol 5000 people had used along with ethylene glycol and glycerol. There are different, see, lysozyme is such kind of protein which crystallizes in many conditions. We had chosen the classic conditions of crystallization, which like one of the earliest condition where people had crystallized. So, what we are going to do? We are going to see, the whole idea is to understand this phase diagram. So, what we are going to do here, we are going to use different concentrations of sodium chloride, let us say 0.5 molar, 1 molar, 1.5 molar, 2 molar, 2.5 and 3 molar, right, different concentrations of sodium chloride along the columns, right. So, every column is having the same concentration of stuff, right. So, if I show you on the plate, so this is how you are going to increase the salt concentration. So, all of these rows like A1, B1, C1, D1, they will have 0.5 molar of sodium chloride, then 1 molar, 2 molar, and on this side we are going to change the pH, different pH, right. So, acetate has the range of like say 3.5 to 5.6, that range the acetate buffer is quite accurate. It works, it acts like buffer, accurate is not the right word, it is buffer in this range, pH range 3.5 to 5.5 let us say. So, we are going to use the pH 3.5, then 4, 4.5 and 5. Now lysozyme, as we know, it crystallizes between 4.2 to 4.8, right, 4.2 to 4.8, that pH range you have the crystals for lysozyme. I expect that you get the crystals in all these three, 4, 4.5 and 5. You might not see crystals in 3.5. I had deliberately kept 3.5 so you really can appreciate a particular pH is essential for lysozymes to crystallize, right. And what we are going to do, right, we are going to have a 3-dimensional phase diagram. 3-dimensional in a sense, you are having the precipitant concentration on one side, right, you are going to have the pH on the other side, right, pH on the other side, right. And what you are going to do, you are going to do in 2 concentrations of protein, one is 10 milligrams per ml, one is 20 milligrams per ml, right. So let me rub it, it's not a very clear thing, so I might have to write it again, the table. Yeah, the first 0.5 molar, 1 molar, 1.5 molar, 2, 2.5 and 3. So that's the salt concentration, and here the pH you have like 3.5, then 4, then you are going to have 4.5 and 5. So this makes your 24 well plate. Now what I said, you are going to have 2 concentrations of protein, one is 10 milligrams per ml and another will be 20 milligrams per ml, right. So this means what, your starting concentrations of protein are going to change, right. We are going to have even more fun with this phase diagram because we are going to make it more elaborate in a sense. So how do you set up the crystallization? You have this cover slip, right, you put a drop of protein, let's say 2 microliters of protein, we set up our pipettes to 2 microliters, we put 2 microliters of protein, okay. Then happens what, you put 2 microliters of your reservoir solution into it, right. Yes, hanging drop, right, but you have to put the cover slip on the table. I'll show you how to do it. You are going to put the cover slip on the table flat, and then you are going to put 2 microliters of lysozyme and you are going to put 2 microliters of reservoir solution, okay. Now we are going to divide ourselves into 2 groups. So one group is going to do 10 mg per ml, another group is going to do 20 mg per ml, right, 1:1. Question 2 is, if I start with 10 mg per ml, when I do 1:1 mixing, what's my starting concentration? 5, right. So when I do 20 mg per ml, my starting concentration will be 10 mg, right, 10 mg per ml concentration, right, 10 mix per ml. This is not it. So you are like 5 people here. So Sonali can join you. So I need 6 people to set up 6 plates. In the first plate, you are going to do 1:1, right, 1 times protein, 1 times reservoir solution, right. The first plate will be 1:1. Let's say we are working with 10 mg per ml concentration. Second plate will be 2:1, 2 times protein, 1 times reservoir. The third will be 1:2. So 3 plates, 1:1, 2:1 and 1:2. You get the idea. So, if I am saying 1:1, you are starting with 5 mg per ml. If I am having 2:1, right, you are not 10 mg per ml, but maybe like 7.5. But if it is 1:2, you are probably starting at 2.5, close to 2 or 3.3, 0.3, one third the concentration. So, you are starting at the phase diagram at different concentrations. So, I will draw again the phase. Can I rub off this grid? Because that phase diagram is extremely important, right. So, that is why I have to redraw that phase diagram over and again. So, if I have to put in again, this is precipitant and this is my protein again. So, you see, by doing the different ratios, say 1:1, probably you are starting here, right. 2:1, you are probably starting somewhere here on the phase diagram, right. Then for let us say a particular concentration of precipitant, right. So, for 1:1, maybe you are starting at this stage in the phase diagram. For 2:1, maybe you are starting at this stage, right. For 1:2, you are probably starting at this stage. So, your starting point on the phase diagram is different, right. The whole idea is you have to hit the nucleation zone in one way or the other, right. Maybe if you start with too high a concentration, you might straight away land up in a precipitation zone. Maybe this is just right, and with this kind of system you might not get crystals at all, right. Such are the kind of conclusions what one draw from the phase diagram, right. These are kind of say conclusions what you are supposed to draw. So, what we are going to do, once we had set up the crystallization, we will learn how to set up crystallization. You have to start documenting them. We have that stereo microscope. You are going to take the images. As soon as you are done with the plate, you are going to take the images of all the wells, right. Now, one group is going to work with 10 mg per ml, another group is going to work with 20 mg per ml, same 1:1, 2:1 and 1:2, right. So, and you are going to set up like salt versus pH 1. So, now you understand the complexity of the phase diagram. So, you have variable as the starting protein concentration plus pH plus salt. So, you actually have a 3-dimensional phase diagram. You understand that, right. So, by having that, so these will help us to have the different starting concentrations, right. And as we are 6 people together, so we are going to do 6 plates. So, one person will say 10 mg per ml, the same 24 conditions. So, acetic acid against the salt concentration, sodium chloride against the acetic acid, different pH, 1:1. The second person, same salt against pH. So, your grid is going to remain the same for all the 6 plates, right. Your grid is going to remain the same. What is going to change is the concentration of the protein which you use and the different ratio of the drop what you make, right. So, you actually now have variable parameters as starting protein concentration, salt concentration, sodium chloride and the different pH. So, you have the 3-dimensional phase diagram. From once you had done crystallization, you see them under the microscope, you take the picture of every well, right. Mind you, you are going to use the same zoom all throughout. If it is set at 2.5, then use 2.5 all throughout your observation, right. So, you should not do like, okay, today I had observed at 2.5 and tomorrow when you come to observe, you make the zoom to 5. The same small crystal will appear big to you. Yeah, oh, my crystal has grown. No, things does not happen that way, right. So, the microscope what we have is from the company Leica. So, the good thing is you can download its software from the website for free, right. You download it onto your respective laptops, you take those images and you measure the dimensions, right. That software will allow you to do it. So, when you start seeing those crystals, we will see how to do those observations, right. So, then happens what? So, you see the crystallization plate as soon as you had set it up, we call it as T0. One is overnight, right. So, tomorrow morning you have to come and observe those crystals, it is extremely important, right. And then say 24 hours, 48 hours like this, but 24, 48 might not be feasible, or if it is feasible then you can come and take the images, right. So, it is going to be 6 times 24 wells, right. See, every plate is having 24, so you have to take images of all the 6 plates, all the 24 conditions, right. So, you have to do that documentation. Now, the data what builds up is humongous, right, but you have to have that, like, okay, how my crystal has grown, and it will happen only if you do this observation in a time bound fashion, right. Then only the phase diagram has some meaning. Now, if you would see the time as the 4th dimension, right, so then you would see, like, okay, you have a multi-dimensional phase diagram, okay. Now, the crystals what you get, I would like to collect the data on those crystals, right, and then let us see how do we go. So, as I said, it is the multiple step. So, siliconization of the cover slip we are going to do, right. So, siliconization is the first part, second is this crystallization, third will be like data collection, right. It is quite interesting how do you do the data collection. So, I am also going to give a small demonstration using the badminton racket here. So, that what happens in the data collection. I am also going to show you physically here, like how the crystals come on those loops. So, those loops where you collect the data pretty much look like tennis rackets, like this table tennis rackets or lawn badminton rackets or lawn tennis rackets, your wish what you want to do. But I have some badminton rackets at home, so I can bring them and show you like what exactly the data collection means, right. Okay. So, then once the data is being collected, we are going to do the data processing, right. So, if you could recall in the CB601 course, so we have the crystal, then you collect the data, then you need the information of all the planes in the crystal. So, you keep rotating the crystal to collect the information for all the planes, right. Now, every time you rotate, you take the image, you rotate, you take the diffraction image, you rotate, you do the diffraction image, that is your data collection. Data processing means you scale all those images to one origin and then you patch them up, right. So, now you have a collated information of all the planes. This is what is required, collated information, right. So, all the planes put together, and once you had done the collation, then comes the model building, right. And we are going to use the molecular replacement method, how to break the phase problem using the molecular replacement, right. Can you recall that? Phase molecular replacement, MAD and SAD, and then MR also, the isomorphous replacement, IR we had done, MR we had done, molecular replacement, and then MAD and SAD, anomalous diffraction or single anomalous diffraction, MAD SAD we had learned. Out of all those, we are going to use the molecular replacement, right. And once the model is being built, how do you go about the iteratively building the model, refining it, building the model, refining it. So, we are going to do all of those things, but one step at a time. Okay. So, I will stop here right now, and then we will now learn how to siliconize, followed by how to set up crystallization.